So it's my great pleasure to start our session of Kyiv Mathematical Colloquium with a talk of Professor Arieh Iserles from University of Cambridge, and he will talk about on mathematical foundation of spectral methods. So please.
Thank you, it is a great pleasure. And let me start by explaining what is a spectral method, or what I and many others mean by a spectral method. So the idea is to solve differential equations, and in my case, I'm interested in solving initial value problems for partial differential equations. So to start with, to have a simple model, I don't want to go into nonlinearities and things like this. This is at least another talk. Let us suppose that we have a time-dependent linear partial differential equation like here. So L is a well-posed linear differential operator generating a strongly continuous semigroup, and the equation is given with some initial and boundary conditions. And X lives in some set omega T is greater or equal to 0. And we're assuming that the solution is living in some separable Hilbert space, which is a subset of L, or is either L2 of omega or subset of the set. In this case, I know this is not a definition you'll find in textbooks, but this is the correct definition. A spectral method is simply an L2 orthonormal basis of H. So I'm using the L2 inner product, and a spectral method is simply a basis of our Hilbert space. And suppose that the basis is orthonormal. And suppose that we have such a basis, the countable basis, so phi n between 0 and infinity, and it is orthogonal with respect to L2, orthonormal. So in that case, we simply approximate the exact solution by a truncated expansion in this basis, in which the coefficients are functions of time. So for t equals 0, the initial condition will be obtained from expanding the initial condition for the PDE in the underlying basis. And then we evolve this unknown u hat n t by imposing Galerkin conditions. So we substitute this truncated equation into the differential equation, and we want the residual to be orthogonal to all the elements of our basis. So we obtain a set of ordinary differential equations which we truncated, and this is our set of ordinary differential equations. It needs to be solved, but as always in mathematics, suppose that we can do it. It is yet again a different lecture. Suppose that we know how to solve ODEs, and we reduce it to this set of ODEs. So these are spectral methods. And now the question is, what do we want from the spectral method? So essentially we want 4 different requirements, which sadly are not always pointing, the arrows that not always point in the same direction. So the first one is stability. By stability, essentially, we mean that as capital N, the number of degrees of freedom, tends to infinity, the numerical evolution operator uniformly tends to the exact operator, and hence the solution is uniformly well posed when the number of degrees of freedom tends to infinity. And this guarantees, according to the Lax equivalence theorem, that our numerical solution converges to the exact solution. If our method is not stable, we don't use it, full stop. This is an absolute requirement. Condition number 2 is preserving the geometry of the solution. So typically, PDEs have a whole range of geometric features which are important both to understand their mathematical behavior and in implementations in physics. For example, some PDEs conserve L2 energy, others dissipate L2 energy. So for example, dispersive equations preserve L2 energy, the diffusion equation dissipates L2 energy. The diffusion equation also is positive. If you start from a positive solution, the solution will be forever positive. Some equations have Hamiltonian forms, and they preserve the Hamiltonian, and there are many other geometric features, and often it is always important, but often essential, to preserve specific geometric features. The third requirement is we want things to converge fast. So we want the expansion coefficients to converge to 0 fast, because this means that we can truncate the expansion very, very early. So, and in general, the advantage of spectral methods is that they converge, the expansions converge or may converge very rapidly, because the faster the convergence, the smaller the set of ODEs we need to solve, and the smaller the set of ODEs, the less it costs. Which brings us to the last step, low cost. So essentially, at the end of the day, we put everything on a computer. The computer is an algebraic machine. All it can do is add, subtract, multiply, divide, and decide if one number is larger than another number. That's all. That's all computers can do. And we want whatever the computer is doing to cost as little as possible, because this allows us not only to save computer time, but also to solve larger problems. And finally, I want one definition going back to preservation of geometry. We say that the spectral method is geometric if it preserves a specific geometric feature of the solution. So for example, if you are solving a linear Schrödinger equation or the Dirac equation, we want to preserve L2 energy, because L2 energy is closely linked to important features of a quantum system that linear Schrödinger or Dirac equation are modeling. So if we have a spectral method for the linear Schrödinger equation that conserves the L2 energy, we say that it is geometric. If we have a spectral method that dissipates L2 energy for the diffusion equation, we're saying it is geometric, and so on. But then there is another definition, which most of my colleagues will say is completely crazy. We say that a method is perfectly geometric if it preserves every single geometric feature of the differential equation, even features we know nothing about. And people will say, well, only God is perfectly geometric. Nothing in computation can be perfectly geometric, and it is not true. Oops. So, are perfectly geometric methods even possible? The answer is yes. And indeed, when you go back in history, the oldest spectral method, and the reason why these methods are called spectral methods, is geometric, except that nobody noticed it. So let us take, for example, an ODE, a linear two-point ODE. So we have this differential operator, P is positive, Q is greater or equal 0. For this is the so we have essentially Sturm-Liouville operator. And because P is positive and Q is not negative, the differential operator is self-adjoint and compact in a finite interval. Suppose we have 0 boundary conditions. And because it is self-adjoint and compact, it has a point spectrum. It has a point spectrum, so it has eigenvalues and eigenfunctions. And the idea is to expand in basis of the eigenfunctions. What can be simpler? So we take the initial condition, we expand it in the basis of eigenfunctions, and we truncate it to capital N. And then the exact solution of the equation with this initial condition is written here. Simply, all it does is each mode is multiplied by e to lambda nt. And this is the exact solution. And because it is exact solution, it preserves all the geometric invariants of the equation automatically. This is a perfectly geometric method. And there are several problems. One is that in general, we don't know the spectrum of L. And also in general, the spectrum need not be a point spectrum. We might well have, say, a continuous spectrum. We no longer have a basis of eigenvalues, eigenfunctions. So all this is of limited use, but let us bear this in mind. And now let us move to, so let us try to understand, to go further into spectral methods. And I want to define one concept which will be central to the analysis, turns out to be absolutely central, the differentiation matrix. So suppose we have an orthonormal basis. And suppose the orthonormal basis consists of C1 functions. And then there exists a natural linear map taking the basis into its derivatives. And so in other words, we can express every derivative phi n prime is a linear combination of the phi case. We can expect, because they form a basis, so there is such a matrix. This matrix is the differentiation matrix of the system. And essentially, the action of this matrix corresponds exactly to the action of the derivative. So in the original space, big L, L2, we have functions in the small L2 space, of which we might be in a subset, where the orthonormal functions evolve. In L2 space of the coefficients of the expansion, this matrix takes functions, takes the expansion of a function into exactly the expansion of the derivative. So it has the same effect as taking a derivative. And this is absolutely fundamental step in approximating differential equations. So this is a differentiation matrix, and note, and this is completely trivial, that provided that we have either zero Dirichlet boundary conditions, or periodic boundary conditions, or Cauchy boundary conditions, so we have a whole line or a whole space, then the differentiation matrix is skew Hermitian, exactly like the derivative is a skew Hermitian operator, or skew symmetric operator, and hence the exponential of t times d is of norm 1 in L2, and the exponential of e t d squared, which corresponds to the second derivative, is less equal 1 in norm, so dissipates. And this is almost an if and only if statement, because the necessary condition for the existence of phi with the skew Hermitian d is that boundary conditions either Cauchy or zero Dirichlet, or slight generalization of periodicity, namely the value at one end is a complex twist of the value at the other end, which actually corresponds as non-trivial. When the twist is 1, it is periodic. When the twist is genuine twist, when kappa here is non-zero, then this occurs in physics, for example, in Bloch waves. And now, so let us see, in this case, how can we design systems with skew Hermitian differentiation matrix. So this is the first requirement. And here we need to distinguish between two situations. First of all, Cauchy problems when we are solving in the full space RD, or for simplicity, I'll do it only on the real line. All this extends to tensor products to several dimensions, and then we'll take other situations. And on the real line, we're using what we called T-systems. So we say that an orthonormal system phi is a T-system if the differentiation matrix is both skew-Hermitian and tridiagonal. Why tridiagonal, you may ask? Because then all the algebraic operations with this matrix are very, very simple and very fast. So in other words, we want this sort of differential recurrence relation. Phi n derivative is a linear combination of phi n minus 1, phi n, and phi n plus 1, consistent with skew Hermitian matrix, and without loss of generality, I can assume that all the bn's are positive and the cn's must be real. That's it. Remember this. This is really fundamental relationship. And now the question is, first of all, are there systems like that? And more than this, given that we're greedy mathematicians, can we characterize all such systems? And the answer is yes. So let us take any Borel measure d mu, which I can represent as w psi d psi, where w is a Radon-Nikodym derivative, and let us Pn be the set of underlying orthogonal polynomials. And as you know, so they are orthogonal with respect to an inner product defined by this measure. And as you know, orthogonal polynomials obey a three-term recurrence relation, and I want the recurrence relation to be as written here, with the same b as c as in the relation over there. B's are positive, as it should be, cn is real, as it should be, and in this case, we set phi n of x equals I to power n over square root of 2 pi, this is a normalizing constant, so that everything is of norm 1, times the Fourier transform, or the inverse Fourier transform of Pn times the square root of the weight function, the Radon-Nikodym derivative. And if the derivative is, if we have an atomic measure and the derivative is, say, linear combination of delta functions, the generalization is obvious. And in that case, I claim that phi n is an orthonormal set in L2, that it obeys this here recurrence relation, and hence its matrix, differentiation matrix is skew Hermitian and tridiagonal. Moreover, every orthonormal basis of L2, which is of the real line, which is tridiagonal skew Hermitian, now the differentiation matrix is tridiagonal skew Hermitian, must be of this form for some measure d mu. But it doesn't mean that the system is a basis of L2. What we want is not just to have an orthonormal system, but we want this orthonormal system to be a basis of this whole space. The answer is it is a basis of the entire space if and only if the support of W is the whole space, or the closure over the support of W is the entire space. So let me give you a few examples. The first example is one that is well known in physics, not that much in mathematics, but in physics. These are Hermite functions. Hermite function, so we are starting from the Hermite measure. The weight function is e to minus x squared of the real line. So the orthonormal polynomials are Hermite functions which are normalized to be of norm 1. And then Hermite functions are simply normalized Hermite polynomials times e to minus x squared over 2. That's all. And these functions are for orthonormal in L2 for a basis, because the support is all of the real line. The C answer 0, because the polynomials have the same parity as n, and Bn is square root of n plus 1 over 2. And theoretical physicists absolutely love these functions for two reasons. First of all, they are eigenfunctions of the free Schrödinger operator, which we'll see later. And secondly, because they are eigenfunctions of the Fourier transform, which we'll see later. And they have many other wonderful features. Second example is spherical Bessel functions. So let us start with the most famous inner product. So Wx lives on the interval minus 1, 1, and there it simply equals 1. The Legendre inner product. And then the orthonormal polynomials are scaled. Legendre polynomials are scaled because we want them to be of rank 1 and of norm 1. And then after we do the transformation with the Fourier transform, we obtained spherical Bessel functions. It is not well known, but easy to prove, that spherical Bessel functions form an orthonormal system in L2. They form an orthonormal system in L2 with a skew-symmetric tridiagonal differentiation matrix. However, the system is not a basis of L2. And it is obvious that it cannot be a basis of L2 because the Fourier transforms of these functions live in the interval minus 1, 1. So the completion of these functions is not L2, but in the Paley-Wiener space of all L2 R functions whose Fourier transform lives in minus 1, 1. So very nice, but we will not use it. Let me move to a much more interesting system, the Marquis-Takenaka functions. So let us take W of x being the Laguerre measure. So it is e to minus x, but defined only for x greater or equal 0. Yes, I know 0 infinity is not the whole real line. The measure is supported on 0 infinity, but wait with it. We'll fix it. And then the orthonormal functions are standard Laguerre polynomials. But the system is not closed in L2, it is closed in the Paley-Wiener space of 0 infinity. However, we are adding to these functions the mirror weight of this weight. So a weight that lives in minus infinity 0, and there it is e to x, which of course decays when you are moving to minus infinity. And then our orthonormal polynomials are Ln of minus x. And then we obtain a system of rational functions of this form here, but the system is indexed not over z plus, but over all of z. These functions are over z plus, these functions are indexed over minus natural numbers. And altogether we have this. Why is this system so exciting? Because once we are looking at an expansion of a function with respect to this system, so the nth coefficient is the inner product of f and phi n, so integral from minus infinity to infinity of f times the conjugate of phi n, everything is complex here, dx, and we make the change of variables x equal half tan theta over 2, we obtain Fourier integrals. And Fourier integrals can be calculated incredibly fast. So essentially, if you want the first m coefficients, it costs you only m log m operations to obtain it to incredibly high accuracy. So this is why this is a very interesting system. Okay, so all this is based on using the Fourier transform, and let me give you a completely different approach to this. And the advantage of this completely different approach is it can be easily generalized to other situations beyond L2. So let us start with phi 0. Take any phi 0, which is a C infinity function on the real line, and all I wanted is that it has a positive Fourier transform which is supported by the real line. That's all. And now what I want is to find real numbers Cn and positive numbers Bn and phi 1, phi 2, and so on, so that we have a system like this that obeys this differential recurrence relation, and these functions phi n form an orthonormal basis of L2. In other words, what we want is a T-system for which phi 0 is given. And turns out we can obtain it, and there is a unique answer to that. And to this end, we have this phi 0, and we say that Kn phi 0 is the nth differential Krylov subspace if it is a span of phi 0, phi 0 prime, up to phi 0 n minus first derivative. So we're taking the first n derivatives counting from 0, we take all the linear combinations, and we obtain a linear space. We call it the nth differential Krylov subspace. The name originates from the fact that standard Krylov subspaces are generated not by derivative operator, but by matrices, multiplication of matrices, vectors by matrices. Here we don't have matrices, but we have a differential operator. And unless phi 0 itself is a solution of linear ODE with constant coefficients, each such space is exactly of dimension n. And of course, by the way we constructed everything, phi n is in Kn plus 1 of phi 0. And this you can easily prove by induction. And now the following proposition is true. So go back to this equation. Suppose that we know phi n minus 1 and phi n. Bn is positive, so we can recover phi n plus 1 from this equation. So phi n plus 1 is phi n derivative plus Bn minus 1 phi n minus 1 minus Icn phi n, all this divided by Bn. So, and suppose that at the moment we know Bn minus 1, Bn and Cn, or we even don't know them, they're just numbers, real numbers, the Bn's are positive. No matter which numbers we are taking here, phi n plus 1 is orthogonal to Kn phi 0. And suppose that we already know Bm and Cm for m between 0 and n minus 1. And we want to advance this algorithm from n minus 1 to n. So we have 2 degrees of freedom left, Bn and Cn, and we want to enforce using them 2 conditions. One is that phi n plus 1 is in Kn plus 2, so this should be is orthogonal to Kn plus 1. So it should be in Kn plus 2, and it should be of norm 1, because it is an orthonormal basis. So we have 2 conditions, and Kn plus 2 here, and we enforce them, and it is an easy formula, and this gives us what we call the differential Lanczos algorithm, which is complete. It is identical to the standard Lanczos algorithm from numerical algebra, which is applied to matrices and to vectors. And now we have a very interesting commutative diagram. So this is a set of what we call seeds. all C infinity functions, phi 0 with positive Fourier transform. Here we have the set of all determinate Borel measures, B. Here we have a set of Jacobi matrices. So essentially coefficients Bn and Cn where Bn are positive. And we have the following commutative diagram. Fourier transform allows us to travel between the seeds and the Borel measures, and this is the measure-theoretic definition of T-systems. The differential Lanczos allows us to travel between the coefficients B and C and the seed. And finally, what is known as the Favart theorem in theory of orthogonal polynomials tells us that for every measure, there is an orthogonal polynomial, and for every set of polynomials that obey the three-term recurrence relation, there exists a measure with respect to which they are orthogonal. So this diagram is commutative, and the beauty of it, it can be extended to other settings. For example, it can be extended to Sobolev inner products, and actually to any sesquilinear product, not even scalar product, a sesquilinear product, for which, for every functions f and g in the space, the inner product of f prime and g plus the inner product of f and g prime is always 0. So this is like integration by parts. So if we have integration by parts, it works. And we'll see examples. So T-systems beyond L2. First of all, Sobolev orthogonality. So suppose that we have an inner product of this form here, some linear combination, we have coefficients alpha L, even infinite number as long non-negative or non-negative, as long as the norm is bounded, the L2 norm is bounded, and here we have derivatives FL G conjugate. And the entire theory generalizes. This is sesquilinear product, and everything generalizes. Hamiltonicity. So suppose that we have a linear Schrödinger equation in one dimension. Here is the equation. So this is the interaction potential. This is the kinetic energy. Everything, of course, is complex. This equation has a Hamiltonian, which is the integral from minus infinity to infinity of mod u prime square plus vx mod u square. This is not necessarily an inner product because v can be negative. And important potentials in physics can be negative, like the Leonard-Jones potential, but it is a sesquilinear product, denoted like that, and we can say this a product of u and u. So if instead of u prime square we have u prime v prime, and here u v, then this is inner product of u and v. So again, we can use the Lanczos algorithm to derive a basis which is orthonormal, quote unquote, because they're not an inner product, with respect to this sesquilinear form. The differentiation matrix is no longer tridiagonal, it is lower Hessenberg, and it is not but it is almost tridiagonal. The elements above the first superdiagonal are very, very small. Okay, what about a finite? Can we extend it to an interval, finite interval? So suppose that instead of minus infinity, infinity, instead of a Cauchy problem, we have the interval minus 1, 1, for example, or AB. And think about it for a second, and you'll see this does not work. So suppose that we have phi n, phi 0, and phi 0 is a C infinity function. And it vanishes at A. That's phi. But the derivative of phi L is d times the derivative of phi. The L's derivative of phi is d times the L minus first derivative of phi. Because we can iterate. So phi prime is d phi. So phi double prime is d square phi. So it is d times phi prime, and so on. So in other words, if all the phi n's vanish at a point, then all the derivatives vanish at this point. And all the derivatives, not only the first, but all the derivatives vanish there. And for example, if phi 0 is analytic, it must be identically 0. But this is a contradiction because it cannot be anymore a unitary, an orthonormal system. So these functions cannot be analytic unless AB is a whole real line. We can overcome this by imposing essential singularities at the endpoints. For example, we can take phi 0 in minus 1, 1 of this form. This is a normalizing constant. And here we have exponential of minus 1 over 1 minus x squared. So it has essential singularity at plus 1 and minus 1. Yes, it is possible to use the Lantos algorithm to obtain as many phi n's as you want. And it's a very bad idea. The very bad idea because the essential singularity causes these functions to develop increasingly large boundary layer near the endpoint. And the functions are becoming completely crazy. And they don't have any power to approximate other functions. This is completely useless. We cannot use it. We need a completely different approach. So let us move to a different approach. And the different approach is what we call W systems. T systems is from tridiagonal, W from weight. So suppose that we have any interval, AB, finite, infinite, I don't care, and we have L2 of AB, and we have a weight function W. A weight function is a function which is non-negative, all its moments are bounded, and the zeroth moment is positive. So in other words, the integral of W is positive. Given a weight function acting in AB, and then it generates an orthonormal polynomial system because it corresponds to the measure W dx. So we have an orthonormal system Pn. The n's W function is simply Pn multiplied by the square root of the weight function. And obviously, the polynomials are orthogonal with respect to the weight function W, so phi n already absorbs the weight function, and hence it is orthogonal in L2. And this is completely trivial idea, but even though it is trivial, it has far-reaching consequences and leads to very non-trivial mathematics. So phi n is orthogonal basis. First of all, is the differentiation matrix skew-symmetric? And the answer is yes, if and only if W vanishes at the endpoints. That's all. In general, the matrix D is not bounded. It is possible to characterize all the measures, all the weight functions for which we have bounded matrices D, and they correspond to so-called Freud measures, but let us not go in that direction. And it is good that it is not bounded, because if it is bounded, then all its powers remain bounded, and then the previous argument about boundary layers near the endpoints still works. We want certain power of this matrix to blow up. So that's good that they are not bounded. And actually, we can somehow regulate the boundedness of powers of D. Remember, for sufficiently large S, we want D to power S to blow up, but for lower powers, we want it to remain bounded so they can approximate, use it to model derivatives up to S minus 1, but not for S. So if WA equals WB, we can write DMN in this form here, with the derivative of the weight function. And then this square is bounded if and only if the square of the derivative of the weight function divided by the weight function is itself a weight function. And so, for example, if we have finite measure, if A and B are both finite, and we define, let's say, W of x is x minus a to some power alpha times b minus x to power beta. So this, remember, A and B are the endpoints, times some new function W tilde, which doesn't vanish at the boundary. Then this square is bounded if and only if alpha and beta are greater than 1. And in general, decay is bounded only if alpha and beta are greater than s minus 1, bounded for every k between 0 and s. So remember, essentially we are interested in 2 intervals now. In general, we're interested in 3 intervals because any other interval can be mapped into one of the 3 intervals. The whole real line, but in this case, we are using t functions. The interval 0 infinity, in this case, we consider W functions from the Laguerre family. So our weight function is x to alpha e to minus x, and in general, alpha has to be greater than minus 1, but we need to take alpha greater than 0 so that W at 0 equals 0. And then Pn, the nth orthonormal function or polynomial, is Ln alpha, but normalized to be of norm 1. And this we multiply by square root of x to alpha e minus x. And the interval minus 1, 1. And now we are using the Gegenbauer family, which is also known under different normalization as the ultraspherical family. Wx is 1 minus x squared to power alpha, where in general alpha has to be greater than minus 1. In our case, again, it has to be greater than 0, so that W vanishes at plus minus 1. And now orthonormal polynomials of this form, Pn alpha alpha is Jacobi polynomial with parameters alpha and alpha, and we have here this normalizing coefficient. And now the question is, what are the differentiation matrices for the Laguerre and for the Gegenbauer family? And turns out, of course, we cannot hope for them to be tridiagonal. This is much too much. But turns out that there are something else which is as wonderful as tridiagonal, but even more magical. So suppose we have a Laguerre family, alpha is positive, as it should be, and then under the main diagonal, dmn is minus 1/2 am bn, where am and bn are given here, and over the main diagonal, so dnm will be plus half, because it is, of course, skew-symmetric. So we have this strange matrix where if you are taking any submatrix of this matrix, which is completely below the diagonal or completely above the main diagonal, the matrix is of rank 1. And matrices like this are very important. They're called semi-separable, and soon we'll read them. What about the Gegenbauer family? Again, alpha has to be greater than 0. And again, dmn obeys the same rule. It is minus half am bn under the main diagonal plus half an bm over the main diagonal, but only when m plus n is odd. If it is even, dmn is 0 because of parity. But now am and bn are different, but all this doesn't matter. This is one of these results that I strongly recommend. Don't try to prove it at home. It is very nasty proof, but these are the results. By the way, not for all weight functions we have this situation. Sometimes it is more complicated, but we will not go into that. Okay, so I say that matrix now is semi-separable. So what are semi-separable matrices? So in general, we say there are many slightly different definitions. Semi-separable, semi-separable generated, and so on. I will now use, to be faithful to all the papers in this area, the definition of semi-separable generated matrix. We say that the matrix is semi-separably generated of rank R if every submatrix, not necessarily square, which is entirely above the main diagonal or entirely below the main diagonal, is of rank less equal R. That's all. And note that for Laguerre W functions, D is semi-separably generated of rank 1, and for Gegenbauer, it is semi-separable. In general, it is semi-separable. For Jacobi polynomials, in general, it is much more complicated proof. It is semi-separably generated of rank 2, but because for Gegenbauer we have all the zeros, once we are looking only at non-zeros, when we separate the odd and even terms in the expansion, it is semi-separably generated of rank 1. And later we'll see why it is important. And moreover, both for Laguerre and for Gegenbauer W functions, the power d to power s is bounded if and only if alpha is greater than s minus 1. And this follows from a very long and complicated combinatorial proof. One direction I already mentioned, but the other direction is much more complicated, but true. So let us move toward the end to fast algebra. So essentially we have 4 different computational steps in this business. First of all, we want to expand the function in the basis. And this can be done for specific T-systems very fast. For Marquis Takenaka, we can expand it using FFT, and this for the first n terms costs us order n log n operations. For Hermite functions, we can use so-called fast Hermite transform, and this will cost us order n times log n squared terms operations, which is still very fast. And we can also do it fast, expanding in Gegenbauer or Laguerre W systems, using modern methods, mostly due to Olver and Townsend, Sheehan, Olver, and Alex Townsend, using asymptotics that give very fast expansions of orthogonal polynomials. Forming DF. So for T-systems, D is a tridiagonal system, so we can multiply D times F in order n operations. D is n by n, or n plus 1 by n plus 1, counting from 0. This is very fast. You cannot do it faster. Also for W systems, as long as we have a semi-separable matrix D, we can do it in order n operations. Later I'll show you how. Solving linear systems generated from the matrix D. So the matrix of the system will be a polynomial in D. Again, we can exploit tridiagonality for T-systems. So if it is a polynomial, it will be a bundled matrix, not necessarily tridiagonal, but bundled. And semi-separability of W systems. Finally, we might want to compute functions of D. For example, the exponential of D to solve the linear ODE system. Or for example, sine and cosine of D if we are solving, for example, something like the wave equation. Well, in that case, we can use the Danforth integral formula using FFT. If there is a time, I'll mention how to do it. And again, this can be done very fast. So everything here can be done fast, provided you do things correctly. So fast matrix vector multiplication for W functions. So suppose that we have this, remember this A and B. So suppose, dmn is either plus or minus half ambn or andm. So let us define two quantities. Sigma m is sum from 0 to m minus 1 bn, fn, and rho m is the sum from m plus 1 up to capital N of an fn. Fn is the vector by which we multiply. And note that, for example, phi m plus 1 is phi m plus bm fm. So we can form these vectors in order n, m operations, order n operations. And now we compute h0 is b0 or 0, hm is this, and this gives us the outcome of the computation of d times the vector f. So in other words, in order n operations, actually sort of, if the matrices are square, order in 6n n operations, including even the final division by 2, we can obtain this multiplication. So in general, to multiply a vector by a matrix costs us n square operations. In this case, it costs us order n. And more complicated argument can be also applied to Gegenbauer W functions, so this can be done very fast. Solving linear algebraic systems. So I'll give the simplest thing to understand is to look at an example. So suppose that we have a 6 by 6 matrix here. So here is this matrix, and this is the right-hand side. So I'm writing it in the compound form, the way we teach undergraduates to do Gaussian elimination. So this is the matrix, and this is the right-hand side. And now subtract from the second row, the first row times A1, A0 over A1 over, so subtract from the first row, the second row, subtract from second row the first row, scale the first row. So subtract the second row times A1, A0 over A1 from the first row. A0 over A1 times A1 B2 is A0 B2. So it will be cancelled. The same here, the same here. What we obtain is this. And then we continue going down the matrix, and by the end of the day, we obtain an upper Hessenberg matrix. Except for the first superdiagonal, everything is 0. And all this has been done in order n operations. And of course, also the right-hand side is changed. And now we repeat exactly the same thing going from the bottom. So in order n operations, we reduce solving this linear system to solving a linear system with a tridiagonal matrix, which we can do easily in order n operations. And all this generalizes to matrices of higher, semi-separable generated matrix of higher rank, and so on. So all this works. Finally, how to compute functions. So we have analytic function G operating on D times V. D is a differentiation matrix. And then we can use the Danforth formula, which is essentially the Cauchy formula, the standard Cauchy formula of complex calculus, except that now this is the resolvent of the operator. Remember, D is a linear operator, is the infinite matrix, or it is a linear operator represented by infinite matrix. So this is the resolvent of D, and the curve gamma has to enclose the spectrum of D with positive orientation. If the spectrum is unbounded, then we need to take half space, for example. So how to approximate this integral? Suppose for simplicity, and this generalizes, the spectrum is bounded. In that case, we have here a curve. We parameterize this curve, and we're choosing roots of unity along the parameter of the curve. And then computing this integral at this equispaced points, the roots of unity, so parametric equispaced points, reduces to a discrete Fourier transform. It can be done with fast Fourier transform. Say, if we are taking capital M points, or the cost will be only just big O of M and log M. So it is incredibly fast. For example, to compute the exponential, suppose that M equals N, we have order N squared log N, which in case it sounds to be expensive, the MATLAB algorithm to compute the exponential costs order N to 4 operations, which is rather more. Finally, I just mentioned that there is an emerging theory of fast convergence, of convergence, because the obvious question, especially from people in approximation theory, harmonic analysis, how fast these orthonormal systems converge. And remember that speedy convergence is essentially this game. A year ago, we didn't know much about it. Now we know much, much more. The knowledge is not complete, but I suppose that I should really wrap up my talk because otherwise I'll never finish. The answer is for W systems, everything is known because everything can be used to the convergence of, or at least with compact intervals like -1, 1, everything is known because everything can be reduced to the Bernstein theorem. I know that Bernstein was not from Kyiv, it was from Kyiv, but I hope it is good enough for you. So, according to Bernstein theorem, if phi n is an orthonormal basis of L2 -1, 1, and both f and all the phi n's are analytic inside this ellipse, where rho is greater than 1. So this ellipse enclosing the interval -1, 1, in that case, lim sup, as n tends to infinity, of f minus the truncated expansion, and we are taking the nth root of this, is less equal 1 over rho. So in other words, the convergence is like 1 over rho to power capital N. And rho is greater than 1. So it is incredibly fast, what is known as spectral or geometric convergence, or exponential convergence. This is not true for T systems, it is not true for W systems on 0 infinity, but in that case, we have an emerging theory, and I don't think I'll have the time to go to this theory. It is mostly an open problem. I will not go into paraspectral methods. Okay, this is, okay, maybe very, very rapid, just to give you an example of perfectly geometric method, because I promised it earlier. Suppose that we have the free Schrödinger equation, so Schrödinger equation without potential. And if you can solve fast this equation, you can solve also fast the Schrödinger equation with potential. So actually, on the real line, we can write the solution of this equation as a Fourier transform. Here we have the Fourier transform of the initial condition, and here times e to it psi squared plus ix psi. So u hat 0 is the Fourier transform of the initial value. So we can write it like this, although numerically it is not a very useful way of doing this. And again, suppose I have an orthonormal basis of L2, so typically it will be a T system, and set this T system, and now define psi n as this integral. Now, what is this integral? If we have, suppose that we are solving this equation with the initial condition phi n, this phi n is the initial condition, then this will be the solution of this differential equation with this initial condition. So this is the solution of the differential equation with the initial condition phi n. And by the way, phi n hat is known for T systems, because this is how we constructed phi n hat. as inverse Fourier transform of its Fourier transform, which was I to power n Pn times the square root of the wave function. So this is the exact solution. And this means that the exact solution of this equation is a linear combination of these functions here. Linear combination, which is determined by the expansion of the initial condition. So if the initial condition is expanded, say, 0 to infinity, un check phi n, the new xt is all you need is to replace phi n by psi n, and of course you truncate both. And this is what you call paraspectral method. And this, so we don't evolve coefficients, we evolve functions. And we don't need to time step even. And this method is perfectly geometric. It preserves every invariant of the solution by definition. Oops. Okay, we can do much more. Essentially, instead of solving the linear Schrodinger, the free Schrodinger equation, we can do it for any linear operator with constant coefficients on a real line or in space RD. But I will not go into that. We can, all this generalizes to multivariate case. Again, I don't have the time to go into that, to RD, to parallel pipettes, to unit balls, to polar coordinates, to simplexes and polytopes, and hopefully, but this is not yet finished, to so-called spectral element methods. That's it, and that's all I had to say.
So thank you, Ari. Let us thank our speaker. Are there any questions?
Yeah, there is no.
No. This.
No.
Say, I have a small question. You
Go
mentioned
ahead.
at the previous page, you mentioned about this Zernike polynomials. Yes. No.
Yes.
Is this for unit disk, or you also have some result for multidimensional unit
Okay,
ball?
so the original Zernike polynomials were defined in the unit disk. And by the way, Franz Zernike got a Nobel Prize in physics for these polynomials.
Yes.
You know, so you don't need to be a great approximation theorist to be better than all the physicists together. But they have been generalized to balls. And also Zernike did it with certain Jacobi polynomials as the kernel. This can be generalized to much more general polynomials and also generalized to units. This has been done by many people.
Yes, you mean when we, instead of this cosines and sines or exponents, we take some spherical harmonics, yes? Or
Well, not really. So spherical harmonics is yet another situation, but spherical harmonics are on spheres, not on balls,
Mhm,
on the surface of a sphere. And this is well known how to do it.
mhm.
So if you have spherical harmonics, you can approximate on a sphere and you don't need all that. There are well-known algorithms and fast algorithms and so on.
Mhm. No,
But inside the ball, it is more complicated.
I, I saw some papers where people leave this Jacobi part. But instead of exponent, yes, they took some spherical harmonics, and in this way they try to extend some results to multidimensional case. This what I mean.
Well, the joke is that when you're solving on balls, the most difficult case is 2 dimensions.
Mm-hmm.
Why? The Laplace operator is wonderful in 1 dimension. In more than 1 dimension, you need to look at the Laplace-Beltrami operator generated by the Laplace operator. And in 2 dimensions, you have a singularity at the origin.
Mm-hmm.
In more than 2 dimensions, the singularity is gone. In 2 dimensions, it is more complicated because essentially, if you are not careful, everything blows up at the origin. In more than 2 dimensions, you don't need to use the 2-dimensional approach because the Laplace-Beltrami operator is stable.
I see. Are there any other questions? Comments? Remarks? So, thank you again for your interesting talk.
My
I-
pleasure.
It was very interesting. Thanks.
And
So, for instance, we are able to use it for different conservation laws in general. Yes?
Well, yes, the perfectly geometric method can be used always. Otherwise, it depends what are the conservation laws. And there are plenty of mysteries here. For example, in numerical solution of ODEs, there is a theorem of Gay and Marsden that says that the only solution of a Hamiltonian system which is both symplectic and preserves the Hamiltonian energy is the exact solution, up to reparametrization. In other words, you cannot conserve under discretization both the Hamiltonian form and the symplectic form. You have to choose one of them, and most people quite rightly would choose the symplectic form because by Liouville theorem it is equivalent to Hamiltonicity. So you have the KAM theory and so on. But in general, geometric features can interact with each other. And this is not something which is well understood.
I just I am just learning. I am obtaining second education in KPI simultaneously in machine learning. So I know about physics informed neural network. Maybe there are some connections between this method and conservation laws in approximation functions by neural networks.
There might be, but they are not trivial. So I know that friends of mine, Carola Shenley, Brynjulf Ovren, and Elena Shvedoni, and their students are working on machine learning using symplectic methods and methods that conserve geometric features. And this leads to better neural network algorithms. So, but one has to ask them, not me.
Thanks. It was very interesting.
Yes, so there is some mileage in bringing structural conservation to using differential equations in neural nets and in pins and physically informed neural nets, but I'm not an expert. Usually when I meet these people, we spend time telling jokes, drinking beer rather than talking mathematics.
Thanks.
Any other questions? So let us thank our speaker again.
Thank you.
I remember you sent me a lot of topics. I hope maybe in future you can make, if
Maybe.
possible, you could make some other talk in some of
Well,
this
the next
direction.
talk will be in Kyiv, not by Zoom.
I hope so.
Well, let's hope for better time. Yes.
Yes. So
Thanks.
thank you, Arieh. I wish you all the
My
best and hope see you in 2D.